All right, students, let's take a look at global climate change. These slides will help you understand greenhouse effect, greenhouse gases, how climate change is studied, reduction of global warming. Let's take a look at some evidence. Do you know the average global temperature has increased by about how much over the past 100 years? This was from your assignment. Correct answer is 0.5 degree Celsius. And we can see that graph here from 1880 to 2010. It has gone up from a -0.2 to 0.5 in terms of anomaly. That means how much it has changed from the norm. And we can see if we go a little further back, there was a little ice age in the 1600s and a little medieval warm period back in the 1000s. We do know that the 2000s have seen twice as many record highs as record lows, so here's some good evidence. And we've seen that 2010 was the hottest January through June on record. And this is another graph showing heat to cold records, many more heat records than we do see cold records. We have lots of new highest max temperature records set in July 2011. We see even more highest minimum temperature records, and that's a big deal. We're saying that not only are the days getting hotter, but they're not getting as cool anymore. And we see here that warm days have been increasing since the 1970s. Warm nights have increased even more, and that is definitely related to the greenhouse effect, because at night, when the Earth is radiating its energy back into space, it is the greenhouse gases that absorb and re-emit that energy back to the planet. Here we see some more temperature changes. Famous graph called the hockey puck graph. And steadily decreasing, going down, but then popping up. I shouldn't say steadily, but on average. This could be related to, partly, Milankovitch cycles, which here we see long-term, going back hundreds of thousands of years. Periodic trend, the oxide level and the temperature, they correlate to each other. And the Milankovitch cycles, there are three things happening here. The orbit is not perfectly elliptical. There are times when the Earth is experiencing more time closer to the sun. And the axis does change its tilt. It becomes sometimes more tilted, and then maybe 10,000 years later, less tilted. And it also spins like a top, very slowly. Every 20,000 years or so, it completes a cycle. Now we can see here some different ice ages that have occurred throughout history. Cool. I'm just going to breeze through these here, but you can certainly pause and take a look at them in more detail. Our last ice age, or yes, glacial period, was 10 to 25,000 years ago. Canada was covered with ice, and it actually got all the way down into Ohio. Or I say that because I'm from that edge right there, northeast Ohio, Akron, Ohio. Go Buckeyes. And nowadays we still have ice, glacial ice covering Greenland. And we'll talk about this word ice sheet for a minute. It means ice that's on top of land. And if that melts, it does contribute to sea level rising, because that water will run off into the sea. But if you say that the seas are going up because icebergs are melting, that is incorrect, because icebergs are already floating in the water, so they don't make it go up any higher. Although I think they do make it go up a tiny bit. But most of an iceberg is already submerged in the water, just the tip that you see. All right, greenhouse effect. Let's start off with a little reminder of the visible light being just a small spectrum of a small sliver of the spectrum. Then we have ultraviolet light, which is higher energy, shorter wavelength, and infrared light, which is longer wavelength, lower energy. And when we talk about light coming into the planet, of all the light, 30% is being reflected back into space, 70% is being absorbed by Earth and then re-radiated as infrared light. Here's another diagram that shows that. I want to focus on this circle right here. This is the back radiation due to the greenhouse gas effect. And if we don't have excess greenhouse gases, then things are in balance and the Earth doesn't get any hotter. Whatever comes in gets re-emitted back out. If we have excess greenhouse effect, we're getting more back radiation to the Earth. Here is just another diagram showing the same thing. Here's another thing showing the same. I guess what I want to point out here is that these are higher energy visible light. This is lower energy infrared, but it's being absorbed by the greenhouse gases. And they re-emit in all directions, including space, and downwards, which is the greenhouse effect. We can see here short wavelength visible light, including some UV and some infrared. And then what Earth is re-emitting back into space is longer wavelength infrared. If we were looking at Earth with an infrared camera, we would see its Earth shine. And here we're just seeing that a lot of these wavelengths from 12 to 16 micrometers are being absorbed by CO2 and H2O. Some of the shorter wavelengths are being absorbed a little bit by these CFC molecules and ozone, which I know that was a big deal with the ozone depletion, but try not to cross the two of them. It just happens that the CFC molecules also act as greenhouse gases, and so do ozone. But don't make the mistake of thinking that because the ozone layer is thinner, that's contributing to global warming, because the UV light that it lets in doesn't heat the Earth much. It is mostly the visible and infrared. Alright, so greenhouse gases. We're going to kind of jump over that. You can pause and read it yourself. But global warming potential. This means the relative ability of one molecule of a given greenhouse gas to contribute to global warming. Which one of the following is not a greenhouse gas? Multiple mark. Ha, I played a trick on you. They're all greenhouse gases, even water vapor. So carbon dioxide is the one that has the biggest effect, but only because it has the most number of molecules. Methane is actually a stronger greenhouse gas, but there's not as many of them. Nitrous oxide is stronger, and hydrochlorofluorocarbon, CFC, being the highest. We can see the levels of all these three here have gone up since 1850s, when we started burning lots of fossil fuels during the Industrial Revolution. They are now at their highest level in 400,000 years, if not longer. The carbon dioxide has increased mostly to burning of fossil fuels. Remember, when we burn fossil fuels, if they burn as cleanly as possible, we would get two things, H2O and CO2. When we have coal, we also get sulfur mixed in there, which makes sulfur oxides. And if we get incomplete combustion because there's not enough oxygen, we would get CO, or even just C, which would be just carbon soot. And deforestation, cutting down trees, removing vegetation from the land, this decreases the sink for carbon. If you don't think this has a real effect, check out this graph. Every year, we are measuring fluctuations in carbon dioxide levels at this particular station in Hawaii. And what season do you think would have the CO2 at a peak? I hope you recognize that would be in winter, when the sun is lowest, so you're not getting as much photosynthesis. In the summer, you have more sunlight, you're getting more photosynthesis, and that helps absorb CO2 from the atmosphere as the plants turn it into sugar and grow. We can see a correlation here, pretty tight, between CO2 levels and global temperature. Another graph showing the same thing. Another graph showing that USA and Canada are the leaders in annual carbon emissions. Oh yeah. Oh yeah. That's right. So we also have Africa here being the least developed country, having very, very small carbon footprint. And want to point out that methane has gone up 151%. What are some sources for methane? You should know this here. One is landfills, anaerobic digestion occurring there. Cattle, you have anaerobic digestion happening in their stomachs. Rice crops, I think we're referring there to the fermentation of rice crops. And fossil fuels, we are mining natural gas, which is mostly methane. As we do that, a lot of it can leak out. Nitrous oxide, nitrogen is from feedlots, chemical plants, auto emissions, agricultural practices. Remember all those synthetic fertilizers being applied to the field. Some of that gets tweaks the nitrogen cycle, and we get more nitrous oxides in the air. We can see all these levels have increased except the CFCs. They went down because, as we saw Ryan Fay signing the Montreal Protocol in his video, that reduced the production of CFCs. And so that effect is declining. I want to talk about radiative forcing, watts per meter square. This is how many watts, how many joules per second of heating is occurring for every square meter of the atmosphere. And we can see carbon dioxide has the biggest effect, not because it's the strongest greenhouse gas per molecule, but because there are many more molecules of them, and methane, nitrous oxide, and CFC. We can see that levels of CO2 and methane have changed throughout history. There's a correlation there, and they change with temperature. There's a correlation there, and I want to talk about that for a minute, because it is kind of a correlation, which is causing which. As the ocean heats up, it is not able to hold as much carbon dioxide, so it outgases. And the same thing happens with fresh water. When fresh water heats up, it is not able to hold as much dissolved oxygen, and that's not good for the fish. If you want to think of it, why does that make sense? Remember that when you're heating up liquids, their molecules are moving faster, and they have a greater tendency to kick out the gas molecules. So we already talked about that, Montreal Protocol. Aerosols, they can also affect the global temperature. They are microscopic particles and droplets in the atmosphere that can warm the climate by absorption. If you think about black soot from burning fuel going off into the environment, or from a volcano. They can also cool the climate by reflection. If you get sulfate aerosols, which are reflective, then they will actually reflect more light into space, causing a cooling effect. And here's a little diagram showing some of those effects here. You don't really have to know these details, but we can see here CO2 has a positive forcing effect of making the planet warmer. So does black carbon, otherwise known as soot. So do these other greenhouse gases. All of them combined together still don't add up to the power of CO2. And then we have reflective aerosols causing a cooling effect on the planet. How do we study climate change? Well, a number of things have been developed. We take ice cores, we dig deep holes in the ground, and we pull out these cores, and we analyze the gas bubbles inside. We can pull out ice from hundreds of thousands of years ago, and pull out air from hundreds of thousands of years ago. And then we analyze it. These cores go back 800,000 years. Basically, every layer, every year, there's a new small layer of ice that's deposited. And when it does it, it also traps in some of the oxygen. I mean, not oxygen, but air. We can also do analysis on pollen. You don't have to know the details there, but they can give us an idea of what kind of vegetation was growing there. And that gives us some indirect evidence for the amount of CO2 in the atmosphere. These are called proxy indicators. They give us approximate values. And of course, direct sampling, like we already talked about. And that's only been done since 1958.